Well, let's now talk about training and testing data. It's very important to split the data in these two groups, one for training and the other for testing. They mustn't be interchanged. This split in the two groups can be done as you want. You can decide to, for example, say the first n rows or records of the data is going to be for training and the remaining for testing, or can be done randomly with different percentage for training and testing, as you will see is done in the breast cancer SPAR program. So the important thing is that separation. You see here the training in yellow color and in the other color the testing. Let's now to introduce a little mathematical notation. As you can see here, our function has been transformed a little in this equation. This is a linear equation where the H hypothesis data X is the value of Y, the prediction that we are going to do, and equal to data 0 plus data 1 x1, where x1 is the feature number 1, plus data 2 x2, x2 is the second feature, and so on until all the features are covered. In the case of the breast cancer prediction, we have nine features, remember? So we go up to x9. So these values of x and data can be seen as vectors going from x0. In this case, x0 needs to be equal to 1 and to xn or feature n, right? Then we have the data values, these parameters, the datas. The terminology in machine learning is going to be coefficients. In logistic regression, these are the coefficients. So to get this formula, we can say that the transpose of the data, that is this one, is a matrix. You can multiply by a vector. If you multiply the transpose of the data or coefficient values by the features, you are going to get again this formula, as you can see here. So we can say that we are trying to calculate the transpose of the data parameters multiplied by the features. So the linear function we just saw is transformed into a signal or logistic function doing some math manipulations shown here to get this final result. And the physical representation of the signal or logistic function is here. Well, we had shown how we convert a linear function, this one, to a logistic function, this one. This logistic function has some properties. For example, the values are always between 0 and 1. This is different from the linear function where the values can go beyond 1 or below 0. Can take any value. And this is an advantage of the logistic function because it doesn't matter if the value is too large, it's going to be closer to 1 but never greater than 1. And if the value is too small, it's going to be closer and closer to 0. One big difference between the linear function and the logistic function is the value returned for this one. The value returned for a logistic regression is a probability. That's a big difference with the linear function. So for example, here we have the prediction for a specific tumor size is equal to 0.7, means that the probability of having a tumor for the given tumor size is 70%. Let's see one more examples about it. We can see here that for different values of a feature, 20, 30, 40, 50, we have different probabilities, 0.7, 23, 85, 99, 4. But in the end, we are returning a prediction as 0 or 1. So this probability has to be mapped to 0 or 1. How is mapped? If the probability is greater or equal than 50%, the prediction is going to be 1. Otherwise, it's going to be 0. Once the function is found, how can we use it to predict values with new real data? For that, the function or the program is going to provide the following values: the intercept and the coefficients. And we need to apply this formula, this part of the formula. So we have the data 0, data 1, data 2, until data n. These are the coefficients. And the first data 0 is the intercept. And we just need to multiply each coefficient by the corresponding value of each feature. Feature number 1, feature number 2, until feature n. This will give us the value of y. We multiply all those values and sum up all of them. This y is called the raw probability. Let's apply this formula to this simple example to see how it works. In this case, we have only one feature, that is the age. And we have these two coefficients, where the first one corresponds to the intercept and the second to the coefficient of the age. We want to predict if a 35 years old person what is the probability to be 1 or to be positive. So we multiply the first coefficient by 1 always, and the second coefficient by the age, in this case 35. We sum up all these two values and we have 0.813. This is the y star, or the raw probability. To get the real probability, what we are looking for, we need to apply this formula that we are seeing here. You can do it in Excel. So that gives us a probability of 69% to be positive if the person is 35 years old. Let's do the same calculations in this second example that corresponds to the values printed for the SPARK program to predict breast cancer. The program prints the intercept and the coefficients in such a way that is not clearly and easy to understand at first sight. The SPARK program prints the coefficients saying that there are 9 features, and of these 9 features, only the feature 1, 2, 5, and 6 have coefficients, and the coefficients are these values: this one, this one, this one, and this one. So we apply the same formula, multiply the intercept by 1, and multiply each coefficient by the value of the corresponding feature, and then sum up all those values, getting the raw probability. We calculate the EXPY, we got 0.3, and the probability is 0.23. The prediction is 0 because this probability is less than 0.5.